Hi everyone, in this video we're going over section 7.4 in your textbook. And what this section is about is you already know that the normal distribution and the binomial distribution look pretty much the same whenever, for the binomial distribution, the n times p times 1 minus p is greater than or equal to 10. In other words, if the variance of the binomial distribution is large enough, then the binomial distribution looks surprisingly very, very similar to the normal distribution. And since the normal distribution is easy to work with and easy to calculate, that's actually an advantage. And there's many cases where if you have a really large sample size for binomial distribution, then you get the same results for using the normal distribution, and while calculating the cumulative distribution function for a binomial distribution is very, very computationally heavy, even for a computer, calculating the CDF for a normal distribution is comparatively easy. So anyways, section 7.4 is going to be talking about the little details that you should be aware of whenever you're trying to approximate a binomial distribution using the normal distribution. So let's jump in. So remember the binomial distribution. Of course, the lowercase n is the number of Bernoulli trials. You can think of it as your sample size of your experiment. P is the probability of success, which is the same for each trial. And when your variance is greater than or equal to 10, and remember the formula for the variance is n times p times 1 minus p, then the binomial distribution is approximated well by the normal distribution. Of course, there's a Desmos link that's going to help demonstrate to us that fact. So you've seen this in several lectures in a row by now, but again, for a large enough variance, your binomial distribution in red and your normal distribution in blue actually look quite alike, right? So let's use a larger value for n so that my variance, which is s squared, is larger than 10. Well, then we find that these match each other pretty closely here. Okay. So let's say that x is a binomial random variable that has a variance greater than or equal to 10. Then we would say that x is approximately normally distributed, even though in truth it's a binomial random variable. If the variance is greater than 10, then it is also approximately normally distributed. The mean of this random variable is n times p, the number of Bernoulli trials times the probability of success for any one of the Bernoulli trials. And the standard deviation is equal to the square root of n times p times 1 minus p. It's the square root of the variance. Now, a normal distribution is a continuous distribution. The binomial distribution is a discrete distribution. So since x is actually a binomial random variable, which is a discrete random variable, if n is 20 and p is a half, then the probability that x is actually equal to 12 is not 0. That's a non-zero probability. And let me show you. So going over here, if I set n is equal to 20 and I set p equal to 0.5, I think that's what my notes is referring to. Yeah, n20 p 0.5. Then the probability that we get exactly 12 from my binomial distribution, well, that is represented by the shaded area inside this vertical rectangle, right? This area here, that area represents the probability that my random variable is actually the number 12 right on the dot. Because this is a discrete distribution, it can only take on integer values. It can only take on the value 9, 10, 11, 12, 13, 14, and so on. But if we're concerned about the number 12, this area here in the box is the probability. Now, a normal distribution is a continuous distribution, and so using the same mean and standard deviation that we get from this underlying binomial distribution, if I were to calculate the probability of a normally distributed random variable being exactly 12, well, that area would be 0, and so the probability would be 0. So to replace my binomial with now the normal distribution, and I'm trying to calculate the probability, which is the area under the curve right whenever x is equal to 12, this area is going to vanish if I let my lower bound and upper bound be 12. And so then there's a 0 probability of getting exactly 12 for a continuous random variable. So you have this discrepancy, right? This thing that's kind of a problem. The fact that a continuous distribution has a probability 0 for a specific value, but a discrete distribution does not have a probability 0 of a specific value. And if we go back to look at the visual right here, we're talking about zooming in for the probability of this continuous normal distribution. As I just look at just the value 12 and we see how that area goes to 0. I think you may already be thinking about the solution. You may already understand what we're supposed to be doing here. Let me go ahead and show you by overlaying the binomial and the normal on top of each other. So I'm going to use this blue curve to approximate this red shaded area in the vertical rectangle. It seems like the smart thing to do would be to extend the lower bound of my normal distribution out to the left just a little bit, and the upper bound of my normal distribution out to the right just a little bit. So hold on, let me figure out why this isn't working really quick. There we go. Okay, so we're going to extend the lower bound of the area under my normal distribution out half away from 12. So we're going to extend it back down to 11.5. And I'm going to extend this upper bound up from 12 up to 12.5. Now this shaded blue area under this normal distribution is actually quite like the shaded red area in that rectangle that I've circled out here. It's pretty much the same. You'll notice that the red rectangle has a little sliver sticking up above the blue area that's not counted by the area under the normal curve. But then again, the area under the normal curve in blue is also counting this triangle that sticks up above the red rectangle. So I think if you took these together, this blue shaded area and this red shaded area are actually about the same. And this is what we're going to do to get a good approximation using the normal distribution, is if I want the probability of exactly 12, I'm going to extend the bounds from 11.5 up to 12.5 for the area under my normal curve. So this is what we call the correction for continuity. What we're saying is instead, we're going to take this probability as the equivalent, the probability that x lies somewhere between 11.5 and 12.5. And because that has some area, of course, it's not equal to 0. And this sort of solves our problem that we had. So this is going to be the area under the normal PDF bell-shaped curve between 11.5 and 12.5. Excellent. This little table is going to show you the little details or the little, things you have to remember if you're going to use the normal distribution to approximate the binomial distribution. And this first relationship is what we've just talked about on the previous slide, how we make that adjustment. Now, if you want the probability that x is less than or equal to some value a from the binomial distribution, we're going to use the probability that that your random variable x is less than a plus a half for exactly the same reason, right? So for the binomial distribution, if we want the probability that it's 12 or less, well, then what we should do is extend the lower bound all the way out to the left, of course, but then for the normal distribution, let's extend it out to 12.5, just so I capture the whole value for 12, right? And so that's what I mean when I say we were going up to a plus a half. Then if you want the probability that your random variable is greater than or equal to a, then we'll use the normal distribution and calculate the probability that x is greater than a minus a half for the same reason. If you want the probability that a is less than or equal to your random variable, which is less than or equal to your upper bound b, again, we're going to subtract a half from the lower bound and add a half to the upper bound when we use the normal distribution to approximate it, because, that's sort of the same kind of reasoning, right? We want to extend a half in the direction that allows us to take up a little bit more area, because the binomial is discrete, the normal is continuous, and we want the best approximation. So in example 1, this says 100 students attempt to kick a field goal at the football field. For every student, we're going to assume a probability of success of 0.2. So I have n is equal to 100, p is 0.2. We're asked the question, what is the probability that exactly 25 students are successful? And if I want this probability, I could use the binomial distribution PMF and evaluate it at 25, but that's not the point of this section. The idea of this section is to actually do the normal approximation to it. And so we'll calculate mu, the mean, is going to be n times p. So my mean will be 100 times 0.2. My mean will be 20. Now my standard deviation is the square root of n times p times 1 minus p. So this is going to be square root, and n times p is 20, so this is 20 times 1 minus p would be 0.8. So 20 times 0.8, I think is 16. So square root of 16, and so that tells me my standard deviation is 4. So I'm looking for a normal distribution with mean equal to 20 and standard deviation equal to 4. That's going to be the normal distribution I'll use to approximate this binomial distribution. And to get a visual of what that looks like, for p is 0.2, and let's see, p is 0.2, n is 100. This is what it looks like, and you can see the binomial in red and the normal in blue. Pretty good approximation. And what you're trying to approximate is, let's see, the probability that exactly 25 students are successful. And so it's going to be, what we're approximating is going to be the area of this rectangle here with the red border, around 25. If we want to approximate that area, the best way to do it is going to be put a lower bound at 24.5 and an upper bound at 25.5 and calculate this area under the normal curve. Just like this. So now this blue area is my approximation, right here around 25. So let's calculate that area using the normal CDF. And I'm going to reference our notes from a previous section. This is my section 7.2 lecture notes that you maybe watched just a couple days ago. And hopefully this is jogging your memory that if I want to find an area under the normal curve between 2 points, I just have to take the CDF, the normal distribution cumulative distribution function, at each of the bounds, upper bound and lower bound, and then subtract the two to find the difference. So going back to our problem, where I'm trying to find the area between 24.5 and 25.5 under my normal curve, that's the strategy I'm going to refer to, is taking the difference between these CDFs. So this is going to be the CDF evaluated at 25.5 minus the normal distribution CDF evaluated at 24.5. And I'm going to need my calculator for this, so let me boot that up. Now we've got my TI-84 here. I'm going to do second VARS. And then I'm going to go down to where it says normal CDF. My upper is going to be 25.5. My mean is going to be 20. And my standard deviation is going to be 4. So that gives me a value of 91.5%. And then I'm going to subtract another normal CDF, this time evaluated at 24.5, with the same mean and standard deviation. And that difference is going to be 0.0457. 0.0457. Or you could say this is about 4.57%. So it's actually a pretty decent percent. Pretty decent chance that exactly 25 students are going to be successful. It's about a 1 in 20, 1 in 21 chance here. But this is going to be your answer that we get using the normal distribution. And this is, by the way, an approximation, the normal approximation for this value. What if we go ahead and just do the exact, right? Just because we're curious about what would the exact binomial be. And so for that, I need to use the binomial probability mass function, so second VARS, and then I go up to, in your calculator, A here. And then the number of trials will be 100. The P was 0.2. The X value we're looking for is 25. And let's see what happens here. I get a value of 0.0438. So it was at least accurate to one significant figure. Not super accurate, but these are pretty close numbers anyways. Not terrible. Not a bad approximation. And what was that? That was 0.0438, I think. All right. Or 439 would be a better way to round that. Okay. New example. This one says 200 students are going to take a standardized general chemistry final exam. For every student, we assume a probability of passing of p equals 0.6. What is the probability that 150 or fewer students pass? So when we say 150 or fewer, we're talking about less than or equal to 150. And this is exactly the kind of problem that the binomial distribution cumulative distribution function was designed to answer. So let's just give the exact answer really quick. We'll start off with the exact answer this time by looking at the binomial CDF, where we have 200 trials this time, 0.6 for my p-value, and 150 for this x value. Just double check I put that in correctly. Okay. Paste and enter. So my exact is, it's very close to 1. 0.9999999. Okay, just extremely close to 1. There's almost no probability left there. So maybe this wasn't a great example. I'll try not to write your test questions to give you answers that are so close to the value 0 or the value 1, but hey, this is just the way it is. And now let's suppose that we want to use the normal approximation. So I'm switching back to my blue pen for my normal approximation calculation. So that's n and this is p. What I'm trying to calculate is the probability that less than or equal to 150 students are going to pass, right? So we want the random variability to be less than or equal to 150. And for the normal distribution, I have a mean of n times p, which is going to be 120, and a standard deviation of square root n times p times 1 minus p. Oops, it's supposed to be parentheses 1 minus p. So n times p is 120, 1 minus p is 0.4, so 120 times 0.4 is 48. Sounds about right. So I'm looking at the square root of 48, which is about 7. Not exactly 7, but you know, square root of 49 is 7, so square root of 48 is just a little bit less than 7. So for my normal distribution approximation here, let's refer back to this table. I'm looking for x less than or equal to 150. To get my normal approximation, I should be looking for the probability that x is less than 150.5, because I have to add an extra 0.5, an extra half, onto my upper bound here. And to do so, let's get the calculator. We do second VARS. We're going to use the normal CDF this time, because I'm using the normal approximation. Now my upper bound is 150.5. My mean, I think, was 120. My standard deviation was about 7. So pasting that in there, and again, I get a number that's very, very close to 1. And it's not perfect. It's not just like the number above it, but it's pretty close. It didn't give me anything really bad for my approximation, right? That's 0.9999341. Here's example 3. It says 300 students take a drug test. For every student, assume a probability of passing of 0.9. What is the probability that 280 or more students pass? So we're looking for the probability that my random variable is greater than or equal to 280. And in the normal approximation here, we're going to look for the probability that x is greater than 279.5. And why would I say that? Well, remember your table here. When you're looking for the probability that p is greater than or equal to 180, well then 180 minus a half would be 179.5. So we're using line 3 from this table. Sorry, that was 279.5. So let me turn those ones into a 2, and that should make more sense. Okay, so my mu, or my mean here, is going to be 3 times 9, which is 27, 270. And my standard deviation is going to be n times p times 1 minus p, which is going to be n times p being 270. 1 minus p would be 0.1. So 270 times 0.1 is 27. And so my standard deviation is just the square root of 27, which is about 5 and maybe a little bit extra, right? Because square root of 25 would be 5, so square root of 27 is just a little bit more than 5. If I weren't so lazy, I would get out my calculator and I would do second square root of 27 and see what I get. And it is, oh, it's actually more like 5.2 than 5.1. So I should be writing 5.2 here since I'm not lazy. Okay, so I've got a mean and a standard deviation. I've got what I should be using for my normal approximation. But again, I'll reference my section 7.2 notes because I want the probability that we're greater than 279.5. So imagine finding this blue area under the curve that's greater than a certain point. The answer to this is going to be 1 minus the normal distribution cumulative distribution function evaluated at 279.5. So that's what I'll do here. 1 minus second VARS, the normal CDF, evaluated at 279.5 with mean, what was my mean? 270? And standard deviation 5.2. So this is a very small number, 0.0339 from the approximation using the normal distribution. What about the exact, right? What about the exact value? So my exact value would be then 1 minus second VRS. I'm going to go to the binomial CDF this time and punch in that I want the probability that it's greater than or equal to 280, which is 1 minus the probability that it is less than or equal to 279, right? And so that is the probability that x is less than or equal to 279. That's exactly what the binomial CDF function is built to do. So then where it says p, this is going to be 0.9. Oops, and that then my number of trials would be 300, and then where it says x value, that's where the 279 goes. And I do paste enter, and I get 0.0287. So back here, I get 0.0287. That's not such a good approximation, is it? That's pretty bad. Let's see, what about my variance, right? My variance here would be actually 27. Oh, that's not a bad variance. Huh, so I'm actually kind of surprised that this particular approximation is so far off the exact value. So, I don't know, oops. Here's example 4. This is what we mean by a normal approximation. It's not exact. Example 4 says 400 students are attempting to bowl a strike at a bowling alley. For every student, the probability P is 0.4. What is the probability that between 100 and 200 students inclusive bowl a strike? So N times P is going to be my mean. So my mean is going to be 400 times 0.4. That's 160. My standard deviation is, of course, square root np times 1 minus p. So n times p is 160. 1 minus p is 0.6. So 0.6 times 160. We'll go ahead and resort to using my calculator so I don't make a mistake here. That's 96. So my standard deviation is square root of 96. Now I know 10 squared is 100, so square root of 96 is going to be just a little bit less than 10 squared, but I'll go ahead and take the square root in the calculator just to be sure, and yeah, it's 9.8. So here I have my standard deviation and my mean. I'm ready to make my normal approximation, but what this question is asking me when I say the probability that between 100 and 200 students inclusive, well, this is saying the probability that my random variable has a value between 100 and 200. But when I say inclusive, I'm including 100 and 200 as part of the winning combination, right? So if x is equal to 200 or x is equal to 100, I'm counting that as part of, my win. Okay, so finding this probability, as I convert it to the normal approximation, I'm going to have to subtract a half from the lower bound and then also add a half to my upper bound, like this. And then I can do this by taking the CDF, evaluate at my upper bound, which is 200.5, and then subtracting the CDF evaluate at my lower bound, which is 99.5. And again, to show you the visual back from our 7.2 lecture notes, what that looks like is this. If I want to find the area in between two bounds, I just take the difference in the cumulative distribution function between the upper bound minus the lower bound. So this is the correct formula. Now I just got to plug it in. So I go to, not that, second VIRS. Normalcdf is number 2. Where it says upper, that's where I'm going to plug in now 200.5. For my mean, I'm going to put in 160. And then for my standard deviation, 9.8. Paste, paste. And then I subtract second VIRS, another Normalcdf, where now my lower bound is what goes in, and my lower bound is 99.5. So this is 99.5 where it says upper. And then I go down to paste, enter, and you get almost all of the probability there, 0.9999821. Not a great example because it's, again, so close to 1, and I'm going to try to make sure that your tests don't have anything that close to 0 or that close to 1. Let's go ahead and take a look at what this would be in the exact case. Never mind, this video is already getting long, and the point of this section is not binomial. You've learned binomial in chapter 6. The point of this video in section 7.4 is how to approximate using the normal distribution, and I think we've already done so. A few more things before I wrap up this video is this table is just actually a repeat of what we had before. Okay, so just what we had before. But if you are asking a probability question about a discrete random variable, there's 2 different ways you could ask the probability question, because the outcome of a discrete random variable has to be an integer, right? So you might ask, what's the probability that x is greater than a? Or as an example, the probability that x is greater than 5, let's say. That would actually be equivalent to asking the question, what's the probability that x is greater than or equal to 6? And these have to be the same because your random variable can't take on any values between 5 and 6. And if you're asked what is the probability that x is less than 7, well, that's the same as the probability that x is less than or equal to 6, right? Because you can't have a value between 6 and 7 anyways, so these are the same probability as long as we're talking about a discrete random variable. And if you're asking what's the probability that x falls between 2 and 8, not inclusive, this is the same thing as asking the probability that x falls between 3 and 7 on an inclusive basis, where we include 3 and 7, right? Right. So going back to this previous table, notice that over here on the left, for this discrete probability question, I always use the inclusive version, so the less than or equal to and the greater than or equal to signs there. And if you happen to get a question that gives you the exclusive version that only has the less than or the greater than signs and not the less than or equal to, you have to use this table to sort of convert between the two. And of course, you don't need to memorize the table if you just use a little bit of common sense and you really understand where this table comes from and why. So take a moment if you don't understand, study this closely and see if you can figure out why. So then here's a new table where I've actually listed the discrete probabilities using the binomial distribution and the continuous estimates using the normal distribution and how you convert between the two probability questions. Well, if you're asking about x less than a, exclusive of a, then we actually subtract a half from the upper bound. And if you're asking x greater than a, exclusive, then we're actually going to add a half to the lower bound. So this is opposite of what we were doing before, because now the probabilities are exclusive instead of inclusive. And again, just like this, we're going to add half to the lower bound and subtract half from the upper bound because of the way I use less than or equal to or just less than, or the way I use greater than and equal to or just greater than. So keep your eyes peeled and think carefully about these questions. I notice that this is, again, this is different from the previous tables. And the last thing, I know I've said many last things at this point, but if your word problem says less than a, or like less than 5, then you're going to interpret this as the probability that x is less than 5 or less than a. If it says a or fewer, that's a sign to use less than or equal to a. If your word problem says what's the probability that it's more than 5, this is the probability that x is greater than 5. If the word problem says what's the probability that a is, or that x is 5 or more, well then that's greater than or equal to 5, right? Between a and b exclusive means you use these signs, and between a and b inclusive means you use those signs. And as long as you're being careful and you're referring to these tables at the end of your notes, you shouldn't be lured into making any mistakes. Okay. Thanks and good luck on your homework.